Welcome to Module 3, Lesson 8, where we will discuss using if-then moves in solving equations. If-then moves. Now, if my memory serves me well, which it doesn't often, I think I kind of blew off a lot of this if-then move stuff from Module 2. But in case you don't recollect or recall the different if-then moves that we looked at and worked with in Lesson 21 of Module 2, we are going to start off by recalling and summarizing the if-then moves. And I am not exactly sure why they are called if-then, but well, I do know if-then, where the if-then stands, but there were a few, and if you know them, you can pause and write them down and come back and check, but if you don't, let's just do it together. Okay, so the first one was the addition. Actually, let me write them down and I'll come back. Okay, so here they are, the if-then moves that we discussed in Lesson 21 of Module 2. And again, like I said, I kind of blew them away a bit, but here we go. We have the four main operations of math: addition, subtraction, multiplication, and division. Okay, and all of those have a property of equality. Okay, all of these have a property of equality. Okay, and all of them are read out or go similarly. Okay, and it starts off with if A equals B, then A plus C equals B plus C. Very simple. So if A equals B and A is 1, that means B has to be 1. Okay? And then if C is 3, then 1 plus 3, of course, is going to be the same as 1 plus 3. Okay? And I think it's kind of straightforward. It might be a little almost to the point of being silly. That of course this is the case, okay, but we'll see how this plays out in this and future lessons. Subtraction says the same. If A equals B, then A minus C equals B minus C, okay, because all these variables have to continue to be the same on either side of the equal sign. Multiplication, of course, again, if A equals B, then A times C is going to be the same as or equal to or equivalent to B times C. One little difference with division, there's another parameter that you have to put into play. So if A equals B and C is not equal to 0, okay, we cannot have a divisor equal to 0, then A divided by C equals B divided by C. Okay, so very important second parameter or criteria for that property of equality, the division property of equality. Okay, so there they are, and you know, there are 8 properties of equality that you will go over or you will see in your during your time working with this curriculum, but we are only interested right now in these 4. Okay, this activity right here, it says it asks you to write the write 3 plus 5 equals 8 and as many true equations as you can using the if-then moves. Identify which if-then move you used. But I'm going to just kind of clarify that and make it a little more specific. If you would go ahead and just use, give me an example of the addition property of equality, the subtraction, the multiplication, and the division. Okay, so give me one of each, and let's go ahead and use the number 4. Okay, use the number 4. All right. Use 4 to help you out. Use the number 4. See if you know what that means. Come on back and we'll do it together. Again, one of each, property of equality, and then use the number 4. Okay, hopefully that wasn't too confusing for you. Just use the number 4. But if we were going to use the addition property of equality, we would just write 3 plus 5 plus 4 equals 8 plus 4. Okay, and if we go ahead and just do that, 3 plus 5 equals 8, plus 4 equals 12, so 12 equals 12. Okay? Now if we do the subtraction property of equality, we have 3 plus 5 minus 4 equals 8 minus 4. Okay, so 3 plus 5 is 8, minus 4 is 4, and then 8 minus 4 equals 4. Okay, so these all prove out. And if we did multiplication, so 3 plus 5 times 4 equals 8 times 4. Okay, so 3 plus 5 is 8 times 4, which is 32, equals 32. Okay, that's the multiplication property of equality. Let me find some room here. Do the division right down here. So 3 plus 5, 3 plus 5 divided by 4 equals 8 divided by 4. Okay, so that equals, of course, 8 divided by 4 equals 8 divided by 4, which is 2 equals 2. Okay, so all of these work out, just examples of the using these if-then moves. And all of these are called the properties of equality, but they describe them here as if-then moves. And the whole idea, and hopefully you're seeing why we're talking about this, is when we are doing or isolating our variable or trying to solve for x, very often we're always doing to the one side what we do to the other. In this case we have multiplied, added 4. Over here we have subtracted 4 or added a negative 4. Over here we have multiplied by 4, both sides, and here we have divided both sides by 4. Okay, it's that whole idea of what you do to one side, you do to the other side. What they're doing is they're giving it a name, and that name is if-then moves. Okay, so when we talk about the if-then moves, it simply means what you do to one side of an equation, you do to the other. If you do it to one side, then you do it to another. If-then. Let's take a look at an if-then statement being an if-then move being used in solving equations. Okay, let's say we had 3x equals 3. The first move we would make, again in terms of isolating x, would be an if-then move, and that would be to, as hopefully you know, is multiplying both sides by the inverse operation of the 3. Okay, or we could write it that way, or we could, these are the same, I kind of prefer this way here, equals, in this case we put 3 over 3, or we would put 3 over 1 times 1/3. Okay, so as you can see, as we talked about a number of times, dividing by a number is the same as multiplying by its reciprocal. Okay, and these are both going to yield the same answer. X equals 1. X equals 1. Of course, this is 1. Right, 1 over 1 equals 1. Okay, so they're both going to yield the same. But that is an if-then move. Okay, yeah, perfect. Okay, so here is our example 1. Okay, let me go ahead and read this out for you. Julia Keller and Israel are volunteer firefighters. On Saturday, the volunteer fire department held its annual coin drop fundraiser at a streetlight. After 1 hour, Keller had collected $42.50 more than Julia, and Israel had collected $15 less than Keller. The three firefighters collected $125.95 in total. How much did each person collect? Okay. Why don't you go ahead and what I'd like you to do first is go ahead and find the solution using a tape diagram. Okay. And that tape diagram should be similar to the tape diagram we made in the last lesson. If you remember, in lesson 7. Okay, and you can go ahead and do it. I'd like you to go ahead and just kind of stack them up. So if you had one that looked like this, okay, and then another one underneath that, and one underneath that. So go ahead and do that, create that tape diagram. And if you need to, maybe go back to lesson 7 and see how we did it there. Okay, so here's how I set it up here. And I want to ask you, if you haven't yet solved it and you're having a little difficulty with setting this up, I just like to ask you why I chose to just leave Julia's as one unknown unit. You can see right there. Well, if you go back and you look at the problem, you see that Keller is being compared to Julia, okay, and Israel is being compared to Keller, okay. So we have something to work off of. Keller, we are able to work off of Julia. We could just write Julia arbitrarily. We can just make a rectangle for her, and then we need to actually make a similar size rectangle for Keller, okay. But we also need to add $42.50 because he made $42.50 more than Julia. Okay, so that's what this is for right here. Now, then they have Israel, and they compare Israel to Keller, and again, we need just to go ahead and have that similar size piece. Okay, and then we're going to add $27.50 here because what we know is that Israel made $15 less than Keller. Okay, so we have to take $15 off this extra bit, so $42.50. Take away 15 leaves us with $27.50. Okay, that's where I got that number $27.50 from. All right, so now we're all set up here, and we can go ahead and solve this. And I won't use algebra, but let's just go ahead and put some things together. So we know we have three units over here. These three unknown units. Okay, all these right here, these rectangles. Okay, these here, these are all equal. Okay, so they're all of equal value. Okay, and then to those three units, we're going to add, $42.50 and plus $27.50. Okay, and this is going to give us the total. Okay, the total for what everyone. This is going to equal that. Okay. So if we know these three units, and we can call them, let's just say 3x, why not? Okay, because they are unknowns. Let's not hide that. Okay, 3x plus, then we have $42.50 and $27.50. We can just add those together, combining like terms. This is 70. Okay, plus 70 equals 125.95. Okay. So there we go, 125.95. And then if we know that we have accounted for 70 already, we could of course take that off of here, okay, because we know how much these are, okay, we still don't know how much these are worth, over here, okay? But we know the three of these are going to be worth this, take away these, okay? Not this one. All right, so then we would have, this is 95, this is 55, 95, okay? So we have 3x equals 55, 95, okay? And again, we could, we'd take the 70 off of that side as well, okay? So 3x equals 55, 95. How do we find that out? We just divide 55, 95 by 3. And we can figure out if this is actually going to be divisible by 3. If you remember, we had the digits. 5 plus 5 is 10, plus 9 is 19, plus 5 is 24. So that will be divisible evenly by 3. And if we do that, we have 1 and then 24. I'm just doing this pretty quickly in my head. I'm sorry. And then 6. Then we have 15 and 5. Okay, so 1865. All right. So we know each one of these is going to be 1865. Okay, using this tape diagram. All right. Again, we knew we compared everything to Julia because she wasn't being compared to anybody. Keller was being compared to her, and then Israel was being compared to Keller. So it just makes sense that we would use Julia as our singular unit here, our unknown, our x, okay? And then Keller was x plus this bit, 4250, because he made 4250 more. And then Israel was x plus 2750, because he had made 15 less than Keller, okay? All right, and we add that all together. We know we had, this was accounted for, this part here, which was 70. If we know it all was 125.95, we took away that 70, left with 55.95. And then, of course, we had 3 pieces to figure out, so we divided by 3, and we got the 1865 each. All right? Operations we used, we added, of course, we added these together, and then we subtracted that 70 away from both sides, okay, or from our total. We got our 55.95, and we did division, okay? So we had to do addition, then we had to do subtraction, and then we finally did division, okay? So 3 operations of math to get that problem done. Okay, again here, so yeah, what were the operations we used to get our answer? And those were addition, subtraction, and division. Okay, so why don't you go ahead and do this one, and this one, and this one, and see what you can do with those, and come on back and we'll talk about them. Okay, so looking at these three problems here, this first one here, the amount. Now they're calling and they want Julia, the money that she collected, to be J dollars. Okay, so J. So Julia is J. Write an expression to represent the amount of money Keller collected in dollars. Of course, it's going to be J plus 42.50 because Keller collected 42.50 more than Julia. So Julia becomes our basis here of all other expressions. Okay, all other terms. All right, so then we went ahead and using the expressions, the next one using the expressions for Julia and Keller, write an expression to represent the amount of money Israel collected in dollars. All right, so we would have so we have Keller here, so J plus 42.50 is Keller, and for Israel you need to subtract away another 15, okay, because he made $15 less than Keller. Okay, so actually if we look at Keller, this is Keller right here, and then you subtract away 15, and that becomes what Israel did. Now you can simplify that, of course, just by simply doing the J plus 27.50, okay, which just takes into account the subtraction of the 15 from the 42.50, right? The final one says, using the expressions written above, write an equation in terms of J that can be used to find the amount each person collected. Now, you might have gone a little bit further than this and actually simplified it and collected like terms. That's great. But the reason I have it out like this because I wanted to show you the three different people. So you have J, who is Julia. J plus 4250 is Keller. J plus 2750 is Israel. Okay, and of course we're adding all of those together, those three people together, and then we an equation because we're meant to write an equation. Okay, so we have equals 125.95 because we know that is the total that was collected. Okay, and this one here I would like to do together, and I'd like you to write it out just like I am, especially those of you who feel you need a little extra work with this, because I want to take this, use many steps here, because when first learning all of this, it is recommended that a teacher, that's me, teach you or show you more steps rather than less at first, okay? And we'll go ahead and explain as we go along. We'll identify what we're doing, okay? So firstly, we have this long equation here. Again, it's separated by each individual, Julia and then Keller and Israel, okay? But we know we have something called any order, any grouping, okay? So we can group all these together. It's also combining like terms is also any order, any grouping. And we can go ahead and get all those J's together. So we could do 3J and get our money together, our numbers here. So plus 70, okay? And that's the 4250 plus the 2750 equals 125.95. Okay, and this is again was any order, any grouping, or also known as collecting like terms. Okay. All right. So next we can go ahead and the if-then move, subtracting 70 from both sides. Okay. This is an if-then move, subtracting. So we have 3J. So minus 70. Okay, equals 125 minus 70, 125.95 minus 70. Okay, and then so 3J equals 55.95. Okay, so this right here was an if-then move. Okay, and it was using the subtraction property of equality. Okay, we're just subtracting 7 from both sides. Again, we could just go ahead and I put it there. There's another step they used with the 0, but we don't really need that. Okay, this is right here is our additive identity right here. But now we're going to do another if-then move. Okay, and you can guess what that is. Another if-then move. We have one more thing to do to this J term. Okay, we need to multiply it by 1/3, which is the reciprocal of the 3. Okay, or divide by 3, which is what we are also doing. Times 55.95. Okay, so that's what we are doing there, and multiplying it by 1/3 or dividing by 3. Okay, and that is another if-then move. The multiplication property of equality. Okay, and this of course is going to be 1J equals, and then if we just did the division, 55.95 divided by 3, we got 18. Who did we get? 18. I'm trying to think what we got here. 1865. I was going to say that, but I think I remembered. 1865. Okay, $18.65, and yeah, we use the inverse here to the multiplicative inverse of 3 to get those. Okay, if-then move, and there we go, and that's our multiplicative identity at the end. All right. So yeah, so if we can prove this is right, because if we know Julia was 1865, then we'd add that 1865 to 4250 to get Keller. So that would give him 6115, and then I guess for for Israel we could just go ahead and subtract. We could do the other way, subtract 15 away from that, from Keller, because that's what they said. 15, what is this, 6? It's 4615. So if we add all these up, these should equal to 125.95. Wish me luck. Okay, 5, 10, 15, 9, 14, 15, 10, 12. There we go. Yeah, we did it. 125.95. So we have proved it by plugging it back in to, actually right here is what I just plugged that all into. J. Okay? Okay, so we know the goal of of rewriting an equation is to rewrite it into the form that says x equals a number, and you can see how we're doing that. Okay, we're trying to get it to x equals some number, and that just means the unknown equals some number. We're trying to get it into this form, and the way we do it is by making zeros and making ones. Okay, so we made a 0 over here by subtracting 70 away, okay, because that equals 0. Of course you don't see the 0 because we don't use it, okay, and then making ones, we did that over here by multiplying by the inverse of 3, okay, and this j down here represents 1, as in 1j, okay. So just keep that in mind as we move into this example 2, okay. Example 2, and again I'm going to read this to you. I just want you to do this first part and then come on back and we'll do a part at a time, unless you feel really good about it and you want to just whip through it yourself. Okay, so here we go. Example 2. You are designing a rectangular pet pen for your new baby puppy. Okay, rectangular pet pen for your new baby puppy. You have 30 feet of fence barrier. You decide that you would like the length to be 6 1/3 feet longer than the width. There we go. 6 1/3 feet longer than the width. Okay? Draw and label a diagram to represent the pet pen. Write expressions to represent both the width and the length of the pet pen. Okay? So you're going to draw and label a diagram. So, of course, what does that mean? That means you're going to draw, just cut to the chase here, okay? You're going to draw your pet pen, all right? I'm going to leave this up to you right now. You're going to go ahead and do the labeling, okay? You need to use some numbers that they have given you here, okay? All right? You're going to do the width equals an expression, then you're going to write an expression for the length of the pet pen, okay? So go ahead and come up back again, just label the pet pen diagram here, and then go ahead and write two expressions, one for the width and one for the length. Okay, so here's how here's how I labeled my diagram here, and you can see that I have x as my width, and then x plus 6 1/3 for my length. And the reason I did that is because they compared the length to the width right here, where it said the length was 6 1/3 feet longer than the width. Okay, so they gave me that. They didn't compare the width to anything, so I don't really have anything to add to the width, so it's going to be my unknown. So if you have a problem like this, the unknown, or that variable, is going to tend to be the one dimension or whatever that is not compared to anything else. So once they compared this length to the width, I knew that it had to be the width plus something. Okay, in this case it was plus 6 1/3. Okay, Something else you might have maybe forgotten to put in here, a very pertinent piece of information, was this idea of the 30-foot barrier, okay? And what that means is barrier is probably another word for perimeter, okay? Your barrier is the thing around an area, okay, which is also called in math a perimeter. So that perimeter or that barrier is 30 feet in length, okay? So if I go from, here all the way around, okay, that is going to be 30 feet of fence, okay? All right, and over here I wrote the expressions. Width was x, and length was x plus 1/3, okay? So now, using those expressions and the perimeter length, go ahead and find the dimensions of the pet pen. Okay, so I want you to find the dimensions, and those dimensions in this case are width and length. Okay, so go ahead and do that. Okay, so I solved it algebraically. I'm not sure, maybe some of you solved it arithmetically, okay, by just using the numbers, but I wanted to show you how to go ahead and do this algebraically, more important to me right now. So firstly, what I did is I know that to get the dimensions, to find the dimensions, I need to place all of my unknowns on the one side, and then my known over here, because I know it is 30 feet. The barrier or the perimeter is 30 feet, is 30 feet of fence. So x plus x, and that's this x here plus this x here, plus x plus 6 1/3, that x plus 6 1/3 side, and then plus that, which is actually over here. Okay, all of those lengths need to equal 30. Okay, what do? I use my any group, any order rule, and which is also combining like terms. Okay, and I have now got all my x's together. I had 4 of them, and then I added the numbers that I had, 6 1/3 plus 6 1/3, or 6 2/3. That equaled 30. Again, I'm going to go ahead and use an if-then move here. I'm going to subtract away that 12 2/3 because I want to make zeros, okay, on one side there. So minus, and do the same thing on both sides. All right, so now I have 4x plus 0, which is the same as 4x. Okay, I made a 0 there. And now that equals 17 1/3 because 30 minus 12 2/3 equals 17 1/3. And then I have, if I do the division, I am dividing both sides by 4, another if-then move. And again, this could be either divide by 4 or multiply by the reciprocal, which is 1/4. Okay, so there you could do an if-then move using either the division or the multiplication. Okay, and I just went, then I got x equals 4 1/3, and I mean, one way to do it would be to, create a, I don't know how you did it, but hopefully you had success with it. But and one way is to look at it and just make a improper fraction, which is 52 over 3. And then if you did that division, you would find that, is there a 52 over 3? 52 over 3, yep. Okay, and you're going to divide that by 4, okay, and you will get 4 1/3, okay. All right. Well, let me just complete that because I'm not sure. Maybe some of you are still a bit confused with that, but hopefully this is something that I'd love for you to be able to know already. But again, I just changed that, and what I'm doing here is I'm just doing this last move here. Okay, I'm dividing both sides, so I know if I divided 4x by 4, I got x. Okay, because I'm creating a 1. But the other side now, a little bit harder to do if you're not real familiar with fractions. But what I did then is I just went ahead and created an improper fraction out of this mixed number here, which is 52 thirds. And now, instead of dividing by 4, I could multiply by the reciprocal, which is much easier. Okay, so if I did this division here, or did my cross cancellation, 52 divided by 4 is 13. Then I could just go ahead and multiply across. 13 times 1 is 13. 3 times 1 is 3. And then I can easily change that 13 thirds into, as you can see, 4 wholes and 1/3 left over. So 4 and 1/3. So that's how you'd go about doing that. Okay? Okay, example 3. Yeah, and again, when you're doing these things, and the way I'm verbalizing what I do, by explaining to you on this in this presentation, I would really love it if you would do the same to your parents, or to your parent teacher, or to someone maybe you're working with. Okay, because verbalizing it really important. All right, so example 3. Nancy's morning routine involves getting dressed, eating breakfast, making her bed, and driving to work. Nancy spends 1/3 of the total time in the morning getting dressed, 10 minutes eating breakfast, 5 minutes making her bed, and the remaining time driving to work. If Nancy spent 35.5 minutes getting dressed, eating breakfast, and making her bed, how long was her drive to work? Okay, so if all of this here equals 35.5, how long was her drive to work? Okay, so she is, our unknown here is this drive to work. Okay, so go ahead and write and solve this problem using an equation. Okay, identify the if-then moves used when solving the equation. Don't worry about any properties that you might be using, but just focus on those if-then moves. And when you're making if-then moves, you are making zeros and you're making ones. Okay, that's what you're doing. So go ahead and try to put these pieces together. You can see some of the numbers that we need. All right, and yeah, come on back. So, well, this one was quite fun. This might have been a bit hard for some of you to set up, okay? But if we just look at the language being used in the problem and reading it word for word, it becomes a lot easier. And just doing it the way it is written out. So for example here, so Nancy, this first line is probably one that some people might have missed, or not first line, but second line. So Nancy spends 1/3 of the total time. Okay, 1/3 of the total time. Now we can make this total time, because this total time is an unknown. We don't know it yet. We do know that those 3 bits, the getting dressed, eating breakfast, and making her bed, we know they all equal 35.5 minutes. Okay, so the way we can actually write 1/3 of the total time, 1/3 of the total time is 1/3 x, which is right here. Okay, and you might have missed that. Okay, so if you want to maybe go back and do it over again without looking at the whole thing, but maybe just looking at the first line, the first expression here, or first equation. Okay, but anyway, so that was 1/3 x. Then of course plus 10, so they're giving me numbers here, and then plus 5. Okay, that comes from the eating breakfast and the making her bed. Okay, and all of that we know, because it tells us in here, is 35.5 minutes. All right, so all we have to do first, not all we have to do, but first we solve that equation. Okay, and if we do solve that equation, we can see what we do here. I just combine the like terms, combine the 10 and the 5 to get 15. Okay, continued on. Then I went and made a 0 on one of the zeros on the left hand side by subtracting away the 15, and I did that the same thing over here. Okay, so now we have a 1/3. We're left with 1/3 x plus 0, but I don't need the 0, equals 20 and 1/2. Now I need to make a 1x. That's kind of a series, part of that if-then move to make a 1 over here, a 1x. So I'm going to multiply by the reciprocal. So the reciprocal of 1/3 is 3/1, or just 3. Okay, and now I went ahead and I multiplied over here also by the reciprocal. 3 over 1 is a reciprocal of 1 over 3 times 41 over 2. So I went ahead and changed this mixed number into an improper fraction. Makes life easier for me. Okay, so now I ended up having x, my 1x, equals 123 over 2, and then I could easily turn that into 61 and 1/2. Okay, because there are 61 wholes in this improper fraction, and then a half left over. Okay, but we're not done yet. Okay, so this is x. This is the entire time, the total time. So the total time is 61.5 minutes. Okay. Now the time, this right here, the time for the getting dressed, eating breakfast in 5 minutes, and making your bed is 35.5 minutes. Okay. All right. Now, if we subtract those away, then we will be able to figure out what her drive to work was, okay? Because there are 4 pieces here. There was the getting dressed, there was the eating breakfast, there was the making her bed, and the driving to work. This 35.5 only accounted for 3 of those things, these 3 things here. Okay, that was 35.5. The whole thing, which we figured out by making this wonderful, wonderful equation here, I hope you're as excited as I am, was 61.5. So all we need to do now is take the whole, subtract it away from those first 3, and then we will come up with a nice number of 26 minutes. Okay, so her drive is 26 minutes, and that is actually the answer to the question. So sometimes you're going to do a lot of work before you even get to answer the questions. You know, all of this work that we did here, it all led to the answer, okay, but it wasn't of itself the answer, okay, but it led to the answer, which is right here. Okay. Now this question here, is your answer reasonable? Explain, is a very, very important one. You can write something down here in your binder if you'd like. I'm not going to require that you do, and I don't check your binders anyway, so only do it if you really want to maybe become better at explaining, which is one of our goals, okay? But thinking about, is your answer reasonable? Okay, well, our answer was 26 minutes, okay, that she took to drive, okay? So if we figure that the 3, the making the bed, the getting dressed, and the breakfast, took 35.5 minutes, it would make sense that a drive would be 26 minutes. Okay, so we know the total time is going to be more than this. Okay, of course, if only 3 activities take 35.5 minutes, then we know the total time is going to be more than that. So anything added onto that truly would be reasonable. Okay, and if you think about it, driving to work generally usually probably would take the longest time. If you're going to drive to work, all right, it's going to have to be somewhat substantial. Okay, thinking in terms of reasonableness. All right, if you only lived like 5 minutes away from home, it's not reasonable that you would walk, but it could be possible. All right, it could be possible, but yeah. So it does indeed look reasonable, and of course, reasonable is relative in this situation. But the way to actually prove it is to go ahead and just plug it all in together, and you'll know that you have the correct answer. But yes, asking yourself for if it is indeed reasonable. Okay. Now, another way to check for reasonableness is to actually use a bar model. Not really a tape diagram in this sense, because not really, well, kind of solving, but using a bar model or kind of a tape diagram. And we could lay it out like this. So we know that dressing is 1/3 of the total time. Okay, so each of these is going to represent a third. Okay, the one thing we do know is dressing is actually going to be a full third. Okay, now we also know that from here, dressing through breakfast, this is also 35.5 minutes. Okay, so that represents 35.5 minutes. Now, if we know that the bed and the breakfast together equal 15 of this 35.5, that means dressing has to be 20.5. Okay, it has to be 20.5 minutes, because we know that this. So this is less. The bed and breakfast are less than the dressing. So we know this has to be 20.5 minutes. I'm going to start using 0.5. You can use those interchangeably if you want. Okay, so it would make good sense that if this third here is 20.5, then this third over here is 20.5, and then you got some extra stuff here, okay, which you don't know yet because you haven't actually solved. But when you're looking for reasonableness of 26 minutes, it would be reasonable to think that because this bit right here, this whole thing is driving. And you can see it looks, it's reasonable to think that that piece could be 26 minutes because it's really close to the same size from here to here as from here to here. Okay, just again checking for reasonableness with a bar model. Okay, so one last example here, and I'll go ahead and read it for you. The total number of participants who went on the 7th grade field trip to the Natural Science Museum consisted of all of the 7th grade students and 7 adult chaperones. 2/3 of the total participants rode a large bus, and the rest rode a smaller bus. If 54 of them rode the large bus, how many students went on the field trip? Okay, so again, look at our pertinent numbers here. We have all of the 7th grade students here, not something that we know. We have 7 adult chaperones. We have 2/3 of the total participants. That means everybody. Okay, they rode the large bus. Okay, and we know that that is actually equal to 54 because 54 rode the large bus. We want to know how many students went on the field trip. Okay, how many students went on the field trip? So go ahead and do your best to solve that, and come on back. Okay, so here it is, just set up, the equation set up. I just want to set it up, and I do want to go through it together. If you're not interested in this, again, just zip to the end or just get to your problem sets. But those of you who would like a little extra instruction, just keep watching. Again, setting up the equation, that is like, the most important aspect of all this, because if you don't set the equation up correctly, then you're not going to come to the right solution. Okay, but the way we set up this equation here is that what we knew, and again we know about the large bus. This is what we know right here. We knew a lot about the large bus. Okay, and that's what we're going to use to help us out. And we know that large bus, there are 54 individuals that rode on it, of all participants. Okay, all right, and then we also know that 2/3 of everybody rode that large bus. Okay, and the only thing we know about the students was that they are an unknown. What we know is we don't know, so we have to represent them with S, the unknown S, and plus 7, because we know that there are 7 adults. Okay, so we know about the adults. All right, so this represents all the participants. That's what's in the parentheses. Okay, and then this represents that 2/3 of them, of everyone, went on the large bus on on which 54 people rode. Okay, so these are equal. 2/3 of everyone is the same as or equivalent to 54. Okay, so from there we can go ahead and start to solve. But once we have that equation set, and again these are all numbers and pieces that are taken from the problem, the 2/3, the 54, okay, the 7 adults, okay, and of course the thing that we don't know that's never mentioned in here is the number of students, so we can go ahead and assign the S variable for students, okay. So again, first thing we could do, any group, any order, any grouping, you know, we could just go ahead and let's just take away that 7 because we can put you know, just put our parentheses anywhere we want because we're only adding and multiplying. So let me just go down here. So I'm going to go 2/3 S plus 7 plus -7. Okay, so I'm creating a 0. And then 54 minus 7. Okay, again doing the same thing on both sides because if then. All right, so now we have 2/3 S equals 47. Okay, and again we're going to go ahead and make, now, well not again, but now we've made our 0. Okay, we made a 0 here by adding the additive inverse. All right, so we did that on both sides. All right, so now we have 2/3. So now to make a 1 out of S, okay, we're going to just multiply by the reciprocal. Okay, all right, and we're going to do the same over here. Actually, 3/2 is our reciprocal because we're looking at 2/3 here. We're getting the reciprocal over 2/3. Okay, so again, of course, we have this is 1S, and that equals, so what is that? 141 over 2. Okay, and 141 over 2, we can know that is, oh, hold on one second. Did I do that correctly? 120. Hold on one sec. Well, I just want to tell you this is a very interesting predicament and something that I don't quite understand right yet, but I will try to understand it and get back to you. While my original equation here is correct, okay, it seems that a problem like this doesn't lend itself to subtracting first, because you notice that I was taking away the 7 first to make the 0, but what I was coming up with is 141 over 2, and as S equals 141 over 2, and that would give me 70.5 or 70.5 students. That just doesn't seem quite right. 70.5 students. So I'm just going to show you what we're going to do here, and this is interesting, and probably a good reason to go back and check. So if I were to go ahead and actually, first of all, 70.5 students is actually silly, okay, because you don't have half the students. So if you end up coming up with an answer like this, you know it's got to be wrong. But if we approached it by first making a 0 by taking away the 7, let's go ahead and make 1 first. And I'll show you why this makes sense actually. So if I went ahead and multiplied 3 over 2 times 2 over 3 on this side and left my S plus 7 intact, okay, because I had said any grouping, any order, but the truth is this actually represents one thing. This actually represents the total number. So it needs to stay together. This is the total number. This is students plus the 7 adults. Okay, so if we do that, then we come up with 1 student plus adult, the 7 adults. So 1S plus 7, that equals, then we go ahead and multiply this side by the reciprocal of 2/3 as well. Okay, and we end up getting 27, and that equals 81. Okay, so 81. So now we have s plus 7 equals 81. So now we can go ahead and make the 0 on this side because this is all by itself. So we can go s plus 7 plus a negative 7 equals 81 minus 7. So that means s equals 74. Sounds like a much more reasonable answer. We can continue to check its reasonableness, by if we went ahead and added the 74 plus the 7, okay, because now we know that's students, that is adults, okay, because we just solved for students here, and we knew adults already was up here, 7. That's 81, which of course we knew from right here, okay, 81, all right. So if we took 2/3 of 81, if we multiply 81 times 2 over 3, okay, let's make myself a little room here. Now we're proving this problem, and that equals, I think we can do that. That of course is 27. That's 1. And multiplied across, that would be 54 over 1, which is 54. Okay, and that's what they said. 2/3 or 2/3 of the large bus was the same as 54 people. Okay, so there we go. There we have it. We've proven it. And again, the reason we had to do it that way, do the division first, was because we've been pretty regularly doing the subtraction first, taking away that number. But in this case, this number was not sitting by itself. Okay, the number 7 here was actually included in its parenthetical expression because it represented one thing on its own. It represented the total number of people on this trip. Okay, total number of people on this trip. So it needed to stay together until it became one unit. Okay, it became one unit here. Okay, down here. Up here it was attached to this 2/3. So that would be the first thing to do there. Okay, hopefully that explains that. All right, and again here we have our lesson summary. Real quick, algebraic approach. To solve an equation algebraically means to use the properties of operation and if-then moves. Okay, those if-then moves, the multiplication, subtraction, division, and addition, okay, properties of equality, all right? To simplify the equation, okay, so that's our goal here, is to simplify the equation into a form where the solution is easily recognizable, okay? We're trying to make it as easy as possible, getting down to the point where you have x equals some number, okay? So for the equations we are studying this year, and all of our equations are called linear equations, okay? And like I just said, we're trying to get it to a point where x equals a number, okay? And where that number is the solution, okay? And again, linear equations. So all of these equations can be plotted on lines, okay? Straight lines, all right? So when we are trying to isolate the x or isolate the variable, that does indeed apply to linear equations. There are going to be times in the future, not this year, but in future algebra, that will not always be the case, okay, to say we're isolating the x because there will be multiple variables. All right, so now these if-then moves, if x is a solution to an equation, it will continue to be a solution to the new equation formed by adding or subtracting a number from both sides of the equation. And again, we're trying to make zeros when it comes to addition and subtraction, okay? And then when it comes to multiplication and division, it will also be a solution when both sides of the equation are multiplied or divided by a non-zero number. And in this case, we are trying to make ones, okay? Trying to make ones when we are multiplying or dividing, okay? Again, we use these if-then moves to make zeros and ones in ways that simplify the original equation. So it's all about simplifying. Okay, and the useful first step is one. This is really good to know and good to maybe highlight. If one is faced with the task of finding a solution to an equation, a useful first step is to collect like terms on each side of the equation. Okay, a useful first step is to collect like terms. Okay, very, very, very important. Very, very useful. Okay, well, I'm sorry this was long, and if you stuck in there until the end, I'm proud of you, and thanks. Yeah, go ahead and get some problem set and some exit ticket done, and you're done.